Welcome to the Explainer. So today, we're basically going to become pattern detectives. We're looking at the fascinating ways we can mathematically predict the future using rules that are, well, literally hidden in plain sight. Nature, art, even just the simple everyday objects around us, they're all governed by these hidden codes. So let's just dive right in and decode the universe together, shall we?
Now, instead of kicking things off with a bunch of dry formulas, let's actually look at the physical world for a second. Let's see if your brain naturally guesses the next step in a pattern. Because believe it or not, long before we write down complex equations, our eyes and our minds are already wired to find order. Let's test that intuition. Take a look at these stacks of tennis balls. Notice how each new triangle is built just by adding the next natural number right to the bottom row, right? So one ball on top, then a row of 2 underneath to make 3, then a row of 3 making 6, then 10 and 15. We actually call these triangular numbers. And I bet your brain already sees that the next bottom row would need 6 balls for sure. The physical shape perfectly dictates the math.
Okay, now let's look at how a totally different physical shape behaves. Here we've got square numbers. Check out the dots. We start with 1, and then we literally wrap the next odd number around it. So 3 odd dots make a 2 by 2 square of 4. Wrap the next odd number, 5, around that, and boom, we get a 3 by 3 square of 9 dots. Add 7, you get 16. Add 11, you get 25. By adding consecutive odd numbers, we miraculously build these perfectly square grids. It's just this beautiful intersection of geometry and arithmetic. Now, to track these patterns without getting totally lost, mathematicians simply use a sequence. It's just an ordered list. Each number in that line is called a term. And to know exactly where a number lives in that line, we use subscript notation. So T subscript 1 is the first term, T2 is the second term, and so on. Basically, this notation is our map. But here's the crucial point. It's incredibly easy to count the first few shapes in a pattern, right? But what if we want to know a massive number, deep into the sequence? Say we need the 1,170th term. We definitely don't want to sit there drawing 1,000 triangles or physically counting millions of dots. Nobody has time for that. We need a mathematical shortcut.
So to crack these sequence codes and instantly jump to any number we want, we actually use two incredible mathematical super tools side by side. On the one hand, we've got explicit rules. These calculate a value purely based on its position in the line. And on the other hand, we have recursive rules, which calculate a value based on the term that came right before it. Let's break down exactly how powerful each of these can be.
Think of an explicit rule as letting us kind of cheat time and jump straight to the answer without needing to know anything else. For example, let's take the sequence of odd numbers. The explicit rule here is UN equals 2n minus 1. In this case, n is the position. So if we want to know what exact position the odd number 137 holds in the universe, we just solve 2n minus 1 equals 137. A little bit of quick algebra tells us n equals 69, and boom, the 69th odd number is exactly 137. Absolutely no counting required.
A recursive rule, on the flip side, builds step by step. Take this recursive rule we have right here. Tn equals Tn minus 1 plus 3. That simply translates to, hey, to get the current term, just take the previous term and add 3. It's incredibly logical, but it does mean we absolutely have to know the previous term to find the next one in the chain. It's kind of like a domino effect. Every single number relies on the one that fell just before it.
Okay, let's move on and see how this builds into something truly spectacular. What if a recursive rule asks you to add the previous 2 numbers together? Well, we start with 1, then 2. Add them up, we get 3. Add 2 and 3, we get 5. Add 3 and 5, we get 8. Then 13, 21, 34. This creates this incredibly explosive compounding pattern that just spirals outward infinitely.
Now, you probably know this famous chain of numbers as the Fibonacci sequence, right? Popularized way back in the year 1200 CE. But look at this timeline. This sequence was actually written down and studied centuries earlier by the Indian mathematician Virahanka, all the way back in the 7th century, and it was further developed by scholars like Gopala and Henmachandra long before it ever reached Europe.
And you know what's brilliantly surprising? It's how Virahanka actually discovered this mathematical code. He didn't find it by crunching abstract numbers on a chalkboard. No, he discovered it by analyzing the rhythmic patterns, the long and short syllables of ancient Prakrit meter and poetry. The fundamental math of nature was literally heard in the rhythm of ancient verse. How cool is that?
So, from ancient poetry, let's shift gears to a highly specific visual application that you can observe right now. Look at this growing physical cross shape of squares. Start with the center, and then really watch how it expands stage by stage. I want you to look closely at exactly where the new tiny squares are being added as the pattern grows. If we take this physical expanding object and map it into raw data, a crystal clear pattern emerges. Stage 1 has 1 square, stage 2 has 5, then 9, then 13. We are adding exactly 4 squares to the outer corners every single time. And because the growth is constantly adding 4, we can define the entire physical system with an explicit sequence rule for n minus 3. With that, you could tell me exactly how many squares are in the millionth stage, instantly.
Whenever a sequence increases, or decreases for that matter, by the exact same constant amount every time, just like our squares growing by 4 or odd numbers growing by 2, we unlock a special, incredibly useful category of math. It's called an arithmetic progression, or AP. There are no sudden leaps here, no wild exponential curves, just steady, reliable clockwork change.
And because this change is so perfectly steady, you can actually predict the future of any arithmetic progression in the universe using this one master explicit rule. Tn equals a plus n minus 1 times d. Now, I know it looks a bit complex, but it's beautifully simple in practice. A is literally just your starting line, the very first term. And d is the constant common difference, the exact amount you step forward or backward each time. And this brilliantly illustrates how all of mathematics is deeply connected. If you take our raw AP data from those growing squares, the 1, 5, 9, 13, and plot those pairs on a standard XY graph, just look at what happens. The dots align to form a perfectly predictable unending straight line. The steady, constant difference in our numbers translates directly to a constant steady slope in visual space. Throughout this explainer, we've decoded the structures of sequences. We've distinguished between recursive steps and those awesome explicit cheat codes, and we've mastered the straight-line predictability of arithmetic progressions. We now have the mathematical keys to find any individual number in an infinite pattern. But I want to leave you with this provocative mystery to explore next. We know how to find the terms, sure. But what happens if you try to add all those infinite terms together? What incredible new pattern emerges when you try to sum the universe? Think about that and keep exploring.